To understand electricity, you really have to understand what atoms are made out of. So they consist of a nucleus that has a neutral charge and positively charged particles. And around that nucleus, you have electrons, negatively charged particles that are orbiting around it. Now, if you are rubbing, for example, like when you're rubbing your hands, you are giving these electrons that are going around the nucleus of an atom energy to leave its orbit. You take him out of that structure and make them mobile. And it's really the flow of these electrons that produce electricity.
So the atmosphere is largely neutral. So you need some energy somehow to break the electrons and away from the neutral atom or molecule. And the way the ionosphere is formed is largely through the extreme ultraviolet radiation coming from the sun. That provides the energy by which you can separate electrons from the atom, and they become free electrons. That atom now becomes positively charged, which is an ion, and that makes up the charged part of the ionosphere, largely from the solar extreme ultraviolet radiation. As we get deeper into the atmosphere, that radiation, it gets absorbed by the upper part of the atmosphere and doesn't reach the surface. You need more energetic particles to further ionize the atmosphere as you get closer to the surface. That's partly brought on by galactic cosmic rays. They have very high energies that can get through the atmosphere, and in that path have a lot of energy, collide with neutral particles and create ionization that way. There's also energetic particles from the magnetosphere that come in, and they also create collisions and create ions in the lower atmosphere. And then finally, at the surface, you have radioactive decay when one outcome is radon. And that radon will come up and emanate from the surface and create charged particles. So the distribution from the surface all the way to the edge of space is variable, but it's this distribution that is so challenging because there's chemistry and there's physical pathways and there's external sources and forces that make it very difficult for us to account for it all. But we know those ions constitute the conductivity of the atmosphere.
I think I should have written a shorter abstract. Okay, so thank you for having me here tonight. It's nice to be back in Edinburgh. So this is where I did my undergrad physics degree many years ago. So tonight I'm going to talk to you about stratiform clouds. So most people, when you say stratiform clouds, they get rather depressed. They think they're the dullest, most boring type of clouds on the planet. And that's probably true, but I get excited by them. Hopefully by the end of this talk, you'll understand why that is. So the reason that we're interested in these clouds is that they're actually electrified. And this is not something that a lot of people know, but by the end of this talk, you will also be experts on this. So the reason that we are interested in these clouds is they become charged, and that charge can influence the cloud microphysical processes inside the clouds, and that may have potential implications for climate. So I'm going to talk you through all that tonight. So we will start off discussing how these clouds become charged, how we know they're charged, and that's through some measurements that we've made with bespoke balloon instrumentation that we've developed at Reading. I'll then discuss what the effect the charge has on the droplet behavior. And then I'll talk about some novel experiments that we've been doing in fogs to demonstrate or to try and find some evidence whether charge affects cloud properties in the real environment. And then finally, I'll discuss what the implications of this are for weather and climate. Because this is very much an understudied effect. It's not included in climate models, and it's not widely studied. So there's lots to learn about it. So we'll start off discussing where the charge comes from, basically. So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. So this charge is being generated all the time. And initially, the charge exists in the form of really tiny nanometer-sized charged ions. But they don't stay tiny for long because they interact with atmospheric molecules and aerosol particles and droplets. And this is the subject of a totally different talk, or three totally different talks, but I just wanted to make you aware that charge can actually affect many different types of aerosol and droplet processes. Some of the things that we've studied, for instance, is the charge effect on long-range dust and volcanic ash transport. So the idea here is that the charge can maintain the dust or the ash in the atmosphere for longer than it would be normally. And this might explain some strange observations of large dust particles that are transported huge distances and nobody can explain why. Another thing that charge might affect is the radiative properties of dust layers. So there's been some theory and measurements that suggest that the particles can align in the electric field and act like a Venetian blind type effect, which affects the amount of solar radiation that's transferred through a dust layer. And then the other thing, which is what we're going to talk about tonight, is the effect of charge on cloud microphysics. So another concept that's important here and that's related to charge in the atmosphere is something called the Earth's global atmospheric electric circuit. So I should probably move this because you can't actually read the title of these slides. So the global circuit, not much better, is it? It's okay, it's fine, good point, it disappeared, sorry. So the global circuit is a hypothetical concept which describes current flow around the planet, basically. Why are we not moving? There we are. Okay, so this was suggested by the Scottish physicist C.T.R. Wilson in the 1920s. So this is the same C.T.R. Wilson who invented the cloud chamber, but he also worked in atmospheric electricity. And in this circuit, we have Earth's surface and the ionosphere, which is a layer in the atmosphere about 60 kilometers up. And these are highly conducting regions. And the idea is that we treat these two surfaces as the plates of a spherical capacitor. And in the middle, we have the atmosphere, which is weakly conducting because of the ionization from the cosmic rays and the radon. And this charge that we have, this positive and negative charge, becomes separated in thunderstorms. So the top of thunderstorms become positively charged and the bottom become negatively charged. And this charge is transferred up into the ionosphere and the negative charge is transferred down to the Earth's surface. This creates a huge voltage difference or potential difference between these two plates of the capacitor, which we call the ionospheric potential. And it's about 200,000 volts. So if you were to connect a wire between the ionosphere and the Earth's surface, there'd be a 200,000 volt difference, which is enormous. And that voltage difference, and because we've got charge carriers, means we have a tiny little current which flows, which we call the air-earth conduction current, or JC. And it flows everywhere. So it's not just related to thunderstorms. It flows in all fair weather regions of the atmosphere. It's flowing right now. So the two things that you've got to remember as we go through this talk, the two concepts are this vertical conduction current, JC, and also the concept of an electric field. So this global circuit sets up an electric field in Earth's atmosphere, which again is everywhere. And near the surface, it's about 100 volts per meter. So that means there's about 100 volts between my feet and about here. We also call it the potential gradient. So I'll use electric field and potential gradient sort of interchangeably in this talk, but they basically mean the same thing. It's just one's the negative of the other. So we've got a conduction current density and we've got an electric field set up by this global circuit.
Hi, this is Jonathan Gardner. I'm going to teach a course on electrodynamics. This is what I learned when I went to college and studied as a physics major. This is real electrodynamics. This isn't hand waving and smiles and happiness and pretending you know when you don't know. The book that we're going to use, and you need to get this even though it costs a lot of money, is Introduction to Electrodynamics. This book is written by David J. Griffiths. It's a great book. This is probably the best physics textbook you're ever going to find in your entire life. This is the second edition. The third edition came out shortly after I graduated. And there's a fourth edition coming out soon. You can find the second edition if you really want it. I don't believe there's too much difference between the different versions. And to be honest, you probably could get by without the textbook. You won't be able to do the problems, of course, which I think is a major part of learning how physics actually works, but you'd be able to learn at least some of the principles and remember them. What do you need to know? Well, if you want to learn electrodynamics, you have to be proficient in the following fields. One is algebra. You know, if you don't know algebra, you're just going to be completely lost. I can't emphasize that enough. You really have to go out there and learn algebra, get used to moving those symbols around. Another is calculus, but you'd be surprised how little you actually need to know to get through everything. So if you just understand the ideas of calculus, what the limit, derivative, and the integrals are, that should be enough. The third thing that you're going to need to know is some classical mechanics. Basically what you would pick up in your first year as a physics student or that physics class you have to take as an engineer. So this is the F equals ma stuff, 1/2 mv squared, some of the rotational kinematics, and some of the basic principles of how physics works. And the reason why you have to take that is you have to understand what mass and velocity and acceleration really mean, and you kind of have to have a feeling for how physicists approach problems versus mathematicians. And the last thing you're going to have to need is you're going to have an open mind. Some of the ideas you're going to learn are completely different than what you think you already know, which is a good thing. When you learn something new, you hopefully eliminate something you thought was true but isn't. So with all of these things, you should be able to do well in this course. Section 233, Poisson's equation and Laplace's equation. So we know that the electric field is just the gradient, or negative the gradient actually, of the potential, the electric potential. So what happens when we take the divergence of E, or rather the divergence of this gradient? So the divergence of E, well, we already know that's going to be equal to the charge density over epsilon naught at that point. And this is also going to be equal the divergence of the gradient, of negative the gradient. So pull that minus sign out. So we have minus the divergence of the gradient of V. So we have basically minus the Laplacian of V. So we get the result that the Laplacian of the potential is equal to the charge density in space divided by epsilon naught. And this is known as Poisson's equation. All this says basically is that the potential basically accelerates. So it grows ever steeper where there's charge around. And Laplace's equation is just basically what you get if you take a region of space where there is no charge. This is called Laplace's equation. And all this says is the acceleration of the potential there is 0. So if it was increasing, it continues to increase. If it was decreasing, it continues to decrease. And if it was flat, it continues to be flat. So much for that. We're going to explore this more in chapter 3. The other interesting thing is what happens when you take the curl of E vector. So that's the curl of minus the gradient of V. Well, no surprise there, that's going to be 0. So the curl of any gradient is, of course, 0. So in truth, the fact that the electric field isn't curly gives us the potential in the first place. So this is basically stating what we already have assumed to be true. Anyway, hope that really helps you.
we have a volumetric charge density contained within a volume V, and the volumetric charge density is rho sub V as usual. And at some point P, we are interested in finding some field quantity, such as the voltage at point P or the electric field at point P. So from what we've just seen, we know that Laplace's equation applies, and if we can solve this equation, given this volumetric charge density, rho sub V, we can find V, and from V we know that we can then find E by going backwards. So this is a challenging problem to solve, or more challenging to solve, because it is again a non-homogeneous differential equation. And it would be easier to solve if the right-hand side were 0. In fact, the right-hand side is 0 in many parts of this problem. If I take this field point, or this observation point, and I move it outside V, so let's say I move it outside of this volume to this point shown here, then actually at that point, there is no volumetric charge density. So the right-hand side is 0, and we get the homogeneous equation that we're looking for. So that equation, where the right-hand side is 0, is called Laplace's equation. So it is a special case of Poisson's equation, and it holds everywhere outside the source region. So everywhere outside this volume V, our problem reduces to solving this homogeneous differential equation, and it basically turns into a boundary value problem. It's important to also realize that we can apply the same concept to many other charge distributions, not just volumetric charge distributions. So the same is true in turning Poisson's equation into Laplace's equation if we had a surface charge density, or a line charge density, or even a discrete distribution of point charges, so long as our observation is not coincident with the charge density itself or the point charges in the case of a discrete distribution, we can turn the problem into solving Laplace's equation. And even with a combination of volumetric, surface, line, and discrete charge distributions, we can apply the same concept.
If you haven't done so yet, make sure you pause the video and try to answer this question on your own first before listening on. We can see that the question is asking us to determine the electric current that's intercepted by the total surface area of Earth. We know from this chapter that electric current is symbolized by lowercase I, and it's equal to the total amount of charge that flows past a given point divided by the total amount of time that the charge takes to flow past that point. Charge is measured in coulombs, and time, of course, is measured in seconds. The question states that about 1,500 protons are flowing for each square meter of Earth's surface per second. And so we can begin to write the current as 1,500 protons divided by 1 second. Now, of course, protons is not the correct unit for charge. As we noted, it has to be in coulombs. But if we multiply by a simple conversion factor, we can get the charge in the correct unit. We know that 1 proton carries 1.6 times 10 to the negative 19th coulombs of charge. And so the protons in the numerator will cancel with the protons in the denominator, and we end up with a value of 2.4 times 10 to the negative 16th coulombs per second. Now, of course, coulombs per second can be simplified to just an ampere, which is a capital A. But that would represent the electric current, again, for each square meter of Earth's surface. So this would be amps per meter squared. In order to figure out the electric current intercepted by the total surface area of the planet, we're going to have to multiply by the surface area of planet Earth. Now, Earth is roughly a sphere, and we know that the surface area of a sphere is 4 pi times the radius squared. Now, the radius of Earth is approximately 6.37 times 10 to the power of 6 meters. So we're going to be plugging that value in for the radius. Now, dimensionally, if we look carefully, we can see that the meters squared in the denominator are going to cancel with the meters squared in the numerator. And so we can pick up our calculators and process this calculation. Don't forget to square the radius, of course. When you do this, you should get an electric current of approximately 0.122 amps. And this would represent the total electric current intercepted by the entire surface area of Earth.